Hey, it's Tom, and today we're going to talk about natural language processing in Apple ecosystem. Why in whole ecosystem, not only in iOS? Because most of the things we will be talking about today are built into macOS, iOS, iPadOS, and even some of them into watchOS. So whether you are writing an app for iOS or for Mac, which will be soon probably the same process, you can use most of them, and they are all built into the system. Some of them are available only in recent one, in iOS 14. That's why today we will be working on the playground in Xcode beta, because some features are only available for iOS 14 SDK. And this video will be probably a little bit long, so I will just add timestamps for particular things, so it might be just easier for you to find interesting topics. Okay, so let's jump to the code. I split available NLP functionalities into some groups, and the first one is text preprocessing, which is most important in my opinion, because those functionalities allows you to preprocess the text before you will use it with the built-in SDK functionalities of other types, or allows you to preprocess text to make it available to be put into some custom model exported from TensorFlow, from Keras, or any other library. Okay, so let's start with text preprocessing. Of course, I prepared all those code to save you time. And the first thing we'll be talking about is language identification. And Apple supports most of the popular languages used around the world. Link to the list of the languages is here. As I mentioned, it will be available down below in the description of the video. So at first, we have to create an instance of NL language recognizer, and this instance will allow us to process strings fetched from some external data or get from user input. And the cool thing is that you can call process string multiple times and it will be still working on the same instance, and it will be remembering the previous state. So if you will put multiple strings of different languages, it will just provide you the dominant language. So for example, if you have two inputs with German language and three inputs from in English, then it will provide you the dominant language as English. And if you want to recognize language from a different source, you can always just reset the current instance and call process string again and again, and it will start recognizing from scratch. So in this case, recognizer will provide us the dominant language, and as far as I remember, it's simplified Chinese. But recently Apple added a new functionality which allows us to get hypotheses for the languages that are the output of the neural network, which is under the hood, and it allows us to get the max set number of the languages which are most commonly detected. So we can specify, for example, maximum 4 elements, but as we see, there are only still 3. So it's simplified Chinese, probably standard Chinese, and Japanese. But as you see, it's 99.9% sure that it's simplified Chinese, and this is why it's being returned as a dominant language. Okay, so that's it. Let's go to another feature. Another important feature is tokenization. It's widely used in natural language processing on most of platforms, and it's important especially if you are working with a language that you don't really know. And there are also some languages that are pretty hard to understand for like people from the West. So nor Japanese, neither Chinese use space to split words. So, for example, this sentence here is a sentence, and as you see, there are no spaces, and there are, as far as I remember, there are 4 words. You can check what's the sentence behind those Chinese letters, and you can just write them in a comment. Let's play the game. And so, for example, if you would like to tokenize as a text, you can tokenize it, so split into different groups. It can be the whole document. You can split the long string into paragraphs. You can split that into sentences, and you can split that into words. So from my experience, words and sentences are those two which are most commonly used, and like in 80% you will just need a word. In 15% you will need cases you will need sentence, and paragraph and document are probably rarely used, or I was just working on a projects that didn't need that. So as in case of language recognizer, we just create NL tokenizer. In this case, we provide a unit, so we want to split that into words. We have to provide the text to the tokenizer, and then we can ask the tokenizer to enumerate the tokens. We provide the start index and end index. In our case, we just want to process the whole string, and as a result, it will output us, as I mentioned, there are 4 words in this sentence, which is the same sentence that was used here, so it's simplified Chinese. Another important functionality is lemmatization. Lemmatization is a process of changing word into this core form. So for example, was is a past form of the core form be. Running is a continuous version of word run. So run and running, in case of NLP, have the same meaning. So they can have the same vector and be treated as the same word. That's why it's important for many models to simplify the words that being put into the process. And in our case, we will need NL tagger, and NL tagger supports many tag schemes. In our case, as you see, we'll be talking about some of them in a moment. In our case, we just need the lemma scheme, and we want to bring this sentence, all the words from this sentence, into their basic form. So we create an NL tagger, we provide the text, and then we just enumerate tags. As in case of the tokenizing sentence, we just provide the unit, and in this case we need word, scheme, it's lemma, and start and end index. So the result of I was running yesterday is it's I, was it's be, running it's run, yesterday it's the same, my it's the form of I, legs leg, and so on. So as you see, these particular sentences weren't changed a lot, but for NLP model it can be crucial to go through this process before putting the sentence into, for example, a neural network. Last functionality in this group is sentiment analysis that was added last year, and it's pretty cool and allows you to quickly find, for example, reviews that need to be checked at first, because it allows you to check the sentiment of the whole sentence or even a long paragraph. And its scale is from -1, which means very negative, to 0, which is neutral, to 1, which is very positive. So as in a previous case, we have to create an NL tagger with a different tag scheme, which is sentiment score. We provide a text, and then we of course get only one result from this tagger, and in this case it's the sentiment score. So as you see, this new iPhone is great. It means it's positive. And if we say that this new iPhone is pure garbage, it will be -0.8, so it's very negative. But new iPhone is great. Let's leave it as it is. Now we are switching into second group, which I called word tagging, and in this group functionality is available for processing natural language, allows us to detect different parts of speech, also different types of entities, and we'll cover that later on. But we'll start with identifying parts of speech, which is very important, because for some languages it's not even important to understand the whole meaning of a sentence. For example, for processing a speech to text, if user is speaking to your phone and you change the sound into text, it might be important for you to just get some key nouns or some key verbs to understand what's the intention behind the words that user just said. And of course Apple allows that, and in this case we just need to create another instance of NL tagger with a different tag scheme, and in this case it's lexical class. We just have to provide the sentence. In this case it's "I love working from home. I save a lot of time on commuting," which is actually true. And then we also have to provide, we can provide some options. In this case we will just omit punctuation and omit white space, because those parts of sentence are not important for us. And as in previous cases, we have to enumerate the text fetched from the tagger. We provide start and end index, a unit, we are interested in words, the scheme, and additional options which can help understand our intention. So in this case, if we will run this code, we will get the pretty long output, and as you see, each word has its assigned part of speech, and it can help us to understand that. For example, we see that our key nouns is home, lot, time. So maybe that's not the perfect case, but for example, if you would consider a help section or frequently asked questions, if your user will provide some sentence into search, then you don't have to exactly match the words, but you can also just get the key nouns. For example, time or key. I lost a key, and if you write an app for some car, you know that it's worth to show the section with information about keys, and that might be very, very helpful. Another important functionality, as I mentioned a moment ago, is detecting, for example, key nouns, and in this case we can be interested in detecting key entities like people, places, or organizations, and even without understanding the whole sentence or the whole paragraph, we can just get some key entities, and it can help us to provide user helpful information or helpful part of our app or content. And it's also available, and in this case we have some text, we create an instance of NL tagger with tag schemes called name type, and we provide the string, of course, some additional options. So we want to omit punctuation, omit white space, and join names, because without option to join names, for example, Steve Jobs would be two names instance, and we just don't want to do that, because in our case it's important that it's one person, exactly like Steve Wozniak and Ronald Wayne. Steve Wozniak probably in US, Steve Wozniak in Poland, because the roots of this person are probably Polish, if I'm correct. Any case, we can also filter some tags, and in our case we can prepare a list of tag types that we are interested. So we are interested in personal name, place name, and organization name, but as you see, there are also others. So yeah, it's really important that if you are interested in that, to just go through the documentation to be sure what's available and what's not. So if we will run this, of course, we just have to call the enumerate tags on the tagger. We see that we just filtered the tags that we are interested in, and Apple is organization name, Steve Jobs, Steve Wozniak, Ronald Wayne, Los Altos is place name, California is place name. And without filtering, of course, we will just get the oh yeah, okay, oh, we can just unwrap that, force unwrap, it should still work. Okay, yeah, so as you see, it's was is other word, founded other word. There are multiple other words that we are not interested in really, so it's just worth to filter them. And yeah, we don't have to unwrap it any longer. And the good thing is that recently we also got availability to check the hypothesis about the words. So as you see, in our case, for oh yeah, we would have to also filter. So yeah, maybe let's do this way. It will be just easier to understand. So Apple, it's organization name, and the confidence for that is 62%, so it's pretty high. There are confidences for other words like the was founded by, and then we have Steve Jobs, which is a personal name, and the confidence is 99.9%. Same with Steve Wozniak, and the confidence of Ronald Wayne is also 99%. And as you see, the confidence about being the place name, like Los Altos being a place name, is also 98%. The California, the confidence of being place name is 97%. So it's pretty okay. And the good thing and a good indicator for us is that the organization name Apple, the confidence is 62%. So the model is not really really sure that it's an organization name. And if the confidence will drop below, for example, 50%, then maybe it's worth to take a look at it and keep in mind that it just might be wrong. Okay, so that's the end of this section. Another important functionality is word embedding, and this is pretty sophisticated, so I decided to make it a separated group. So word embedding in a shortcut is changing a string, which is word, into a vector, and thanks to being a vector, it's much easier to compare the word with other words, to find similar words. It's just like mapping a word into some multi-dimensional space, and then it makes it easier to find a similar words and compare two words if their meaning is similar or not. Okay, so and it's supported in 7 languages right now, English, Spanish, French, Italian, German, Portuguese, and simplified Chinese. So the first functionality in word embedding is just getting a vector for word, and as you may see, it's really multi-dimensional. It's over 500 parameters in this vector, if I'm correct. And right now, you will probably don't know what to do with that, but let's go further. Another really interesting feature is getting distance between two words. So we can create a new instance of NL embedding. We have to provide the language that we want to use. So it's, if you have an input from user, it's important to run language identification at first, and then you will be sure which language you should choose for word embedding. And then we can use this NL embedding to measure the distance between two words. And couch and sofa are words that are pretty close each other. So the distance is 0.56, and for example, chair should be also pretty close. Yeah, but it's 0.72. But if we'll use, for example, egg, that's for sure much further from the sofa meaning. And this is how you can compare two words if their meaning is pretty similar or not. And that might be useful to just get, for example, some suggestions in a search bar or in any user input. Another important feature is getting nearest neighbors, because that's really useful, especially when you are creating an app in which user has to search through some list of items. And for example, if user will write chair, and you have an app that is available to sell different furnitures, you can also show him different categories or different words that are close to this word provided by this user. And in this case, we also create an NL embedding instance, and we call enumerate neighbors for this word. And we can also provide the maximum count of the words that will be returned. So in this case, we have sofa, couch, armchair, chaise, settee. And as you see, I also printed out the distance between those words, and they are all pretty close together. The example with sofa and couch we were working in a previous case is also here. So that's pretty cool. And of course, sometimes you can also have multiple inputs. So you would like to get nearest neighbor not for word, because for example you have two words, but you want to get a nearest neighbor for vector, because you can add vectors. For example, you have two inputs. One is couch and the second is window, and you want to get some words with similar meaning to show, for example, different furnitures or different elements of a room. So you can just add those two vectors and create an NL embedding instance, of course, and enumerate neighbors for this vector. This newly created vector is just a sum of the vector for couch and the vector for window. And let's see what will be returned. So couch, window, of course, because the newly created vector is a sum of the couch and the window words, so it's not a surprise. But then we have also sofa, armchair, and doorway. So yeah, as we see, not all words are connected only with couch, but the doorway is probably more connected with window than with couch. And that's it in the word embedding section. Last group of built-in functionalities is sentence embedding, and it appeared recently. It's available only in most recent SDKs. That's why if you want to work with that, you just need to use Xcode beta. As for now, it's July 2020. So sentence embedding is working in a very similar way as the word embedding, but it's available to work on a whole sentences. So it understands much more than just simple word embedding. And in this case, we have very similar functionalities. So we can get a vector for sentence, which we may use in future processing. For example, we can also add the vectors for different sentences and then compare that with some other one. And in this case, we just get a vector which is pretty similar to a vector that we have seen for word embedding. Much more interesting feature in this case is computing distance between two sentences, and it may be also helpful in help section, in frequently asked questions. You can just compare, for example, headers of the help section with the input provided by user. So we also create NL embedding, but we create an instance for sentence embedding, not word embedding. And then we can count distance between two sentences. So as you see, those two should be pretty close. Maybe not so close. I'm working from home and he's working in the office. But in general, they have something in common. They are both talking about working. And if he will be working from home too, then I believe the distance should be smaller. Yeah, as you see, it's 0.6 comparing to 0.94. Okay, there are also a couple others functionalities built into NLP, natural language framework, but they all demand using CoreML, or there are also some that are very unpopular and only few people will be using them probably. So I hope that for most users this is totally enough information, and it should help you to understand the natural language framework and to start working with that, because NLP is very interesting, especially why in the apps, for example, while providing the data to user and working on a data got from user. Okay, so that's everything I prepared for you today. I hope you enjoyed the video. Link to this playground on my GitHub will be down below in the description. If you have any questions, let me know in the comments section. I will be more than happy to help you, if I will be, of course, able to help you. And see you next time. Have a good day. Bye.